Welcome! Today we'll start with the introduction of volume integrals, and similar to the one-dimensional case, we'll start with a very special type of volume integrals. Specifically, we will introduce the integral over boxes in higher dimensions. So that's somewhat of the analogon of intervals in one dimension. So this is section 15.2, volume integrals. And as the name suggests, what we want to do here is we want to be able to compute the volume between a function's graph and the variable plane. Yeah, so that's what we want to do, compute volume between, let's just say, the domain and the graph of a function. And let's recall how this was introduced in one dimension. We defined the integral there. So for a function on R, what we did basically was something like the following. So we had the graph of a function. Let's say that function might look something like this. And we wanted to integrate that function. What we did to define that integral was we divided the x-axis into intervals like this. Intervals on x-axis. So we partitioned our domain into intervals. And then we had a look at the boxes that were defined by these intervals and the function. So we drew rectangles, right? Rectangles like this. And what we did next was define two particular rectangles, or the areas. One that is below the graph. So we took for each of those areas here, each of those intervals, we took the lower bound of the function on an interval, this one for example, or this one here, and we drew the rectangle. So that would be this rectangle here, or this rectangle, this one, or this one. And we also used the upper bound. So we also looked at this rectangle, this one here, and this one. Yeah, so we bounded the real area from below and from above. And by then just making these intervals smaller and smaller and smaller, we defined a limit process. And we said if the limit actually exists, then we call the value of that limit the integral of f over that domain. Okay, so the main points. We bounded the area from above and from below through rectangles, and then we just decreased the interval length. And if both bounds, for the green rectangles and for the orange rectangles, if those both bounds converge to the same value, then we call this the integral. Both bounds converge to the same value, then this value will be the integral. integral of the function f. That's basically the process for functions defined on the real line. And we'll now try to mimic that very process in higher dimensions as well. And instead of intervals, we are just going to use boxes. We're going to use boxes on the x1, x2 plane, or boxes in higher dimensions, boxes on the domain where the function is defined. And then we can also define boxes of one more dimension that bound this volume from above and from below. We can easily compute the volume of those boxes, and then we'll decrease the size of the boxes and see if that process converges. Okay, so the idea is, instead of intervals, we will use boxes in R to the n. And let's first define what precisely we mean by a box and how we measure the size and the volume of a box. So that's the first thing that we need to take care about. It's a definition. So let's first define what a box is. Now, a set B, subset of R to the n, is called a box if there exist vectors, we denote these by A, with the components alpha 1 to alpha n in R to the n. And we also need a vector B, beta 1 to beta n, also in R to the n. We will require that A is less or equal to B, and that means alpha I is less or equal to beta I for all I. So all components are less or equal in vector A than B. And we want those vectors to define the set, so such that the set B can be written as the Cartesian product of the intervals defined by those vectors here. So we'll start with the interval alpha 1, beta 1. Then we'll take the Cartesian product with the interval alpha 2, beta 2, and so on up to alpha n, beta n. So that's precisely what hopefully you would imagine if you think of a box. We use the following notation for that. So this box B will be denoted as B of A and B if we want to express the vectors that define that box. Okay, so very simple example of such a box. Imagine something like this here. That could be a box. Right, and in this case, for example, the vector A would be here. Okay, so that's precisely the vector A. The lower bound of those intervals. The vector B would be here. So this here is the interval from alpha 1 to beta 1, for example. And this here would be the interval from alpha 2 to beta 2. Okay, so we just take the coordinates of those vectors, those defined intervals, and the cross product of those intervals. That's what we call the box. And of course, it's easy to define a volume for such a box, or to compute a volume for such a box. So for a box B, AB. The volume is denoted by vol of B of A and B, and that is simply the product of the side length of these boxes. So what we need to do is we need to take the product of those side lengths, and that is simply beta I minus alpha I. Remember, beta is always the greater coordinate. So beta I minus alpha I is the length of one side of the box. We just multiply all those lengths to get the volume. And we also define what we call the diameter. The diameter, that will be denoted by diam of B, AB. And by that we'll measure the size of the box. So that's something like the length of an interval. We'll define this to be B, the norm of B minus A, right? So again, for a simple box like this, where we have A here and B here, the diameter of that box is the length of this line here. Okay, so that's the diameter of BAB. And the volume of that box is, of course, simply the area here, yeah? So in this two-dimensional case, it's just the same as the area. That is the volume of BAB. Okay, now that we can kind of measure the volume and the size of a box, we can define what we mean by refining a box. So for the intervals, we just decrease the length of the intervals. For the boxes, we use the diameter as the relevant measure. And what we do is we just take a box and we'll subdivide it into smaller boxes. And we'll call that a partition. Okay, so let B subset of R to the n be a box. And then we'll define a partition, or sometimes called a rectangular partition. We call that P usually of B is a finite set of boxes we'll say boxes 1 to M such that the following two things hold. First, the union of all those boxes in the partition. So if we take the union K from 1 to M of those BK, then we get back B. So together they make up the original box B. And the second, if we intersect any of those two boxes, then their intersection is almost empty. The boundaries may, of course, overlap. So the precise definition is the interiors do not overlap. So the interior of BK intersected with the interior of BJ is empty for all J not equal to K. And we'll also define the diameter of such a partition. The diameter of a partition P equals B1 to BM is defined as, and we'll just say the largest of the diameters of the boxes that make up the partition. That's what we call the diameter of the partition. Okay, so diameter of P is defined as the maximum of the diameters of those boxes B1 to Bm. So we maximize that over K. Okay, again, let's see what that means. Let's say we have a box here. Looks like this. And then we can partition that box. What that means is, well, we just partition it into smaller units like this, for example. And then maybe one more here and one more here. Okay, so those would be the boxes that make up our partition. Like this could be B1, B2, B3, B4, B5. So that's a partition into 5 boxes. And the diameter of that partition is equal to the largest diameter of those 5 boxes. And that should be that B5 box here. So that would be the diameter of P. And finally, to conclude the definition of those boxes, we'll also need a notation for the set of all possible partitions of a box. So we'll introduce that for a box B, subset of R to the n, the set of all partitions of B is denoted by P of B. So now we know what a box is. We know how to measure the size of a box, namely by using its diameter, and we know how to subdivide a box. So we take a partition, and we can measure the size of that partition again by its diameter, by the diameter of the largest box. So what we do for the integration is pretty obvious, I hope. We take the domain, we'll subdivide it into boxes, and then we can, on each of those boxes, we can then define the volume between that box and the graph of f. Or more specifically, we can define a lower box, lower bound for that, by taking the infimum of f over that box, and we can define an upper bound by taking the supremum of f over that box. And again, we'll then take smaller and smaller partitions when the diameter decreases, so the boxes become smaller and smaller, and hopefully those two measurements, the upper and lower bound, is converging. And if that happens, we'll call this value the integral or the volume of that graph f. Okay, only restriction so far. To start off, we need a function defined on a box, because so far we can only partition boxes into smaller boxes. Yeah, we cannot work with arbitrary or even infinite domains yet. But we'll, of course, be able to extend that definition a little further in one of the next videos, as usual. But let's first define what an integral of a function over a box is. So that's the main definition here, definition of the integral. So we start with a box, let B in R to the n be a box, and f a function defined on that box that maps to the reals. Then we can first define those upper and lower bounds. So for a given partition P in the set of all partitions of that box, the upper and lower Riemann sum. So these bounds will be called Riemann sums. Is defined as the following. We'll start with the upper bound. We'll denote that by sigma plus of f and p. And that is simply defined as the sum over all boxes bk in that partition P. And for all of those boxes, we'll compute the supremum of f of x over that box. So we'll take the highest function value or supremum of that value over that box, and we'll then multiply this with the volume of the box bk. Right? So we extend the box by one dimension basically and make it high enough so that it just includes all of the graph in that box. That's the upper Riemann sum. And of course we can also define the lower Riemann sum in an analogous way. Sigma minus of f and p. And that's defined as bk in p. Sum of the infimum of the f of x in bk times the volume of bk. And of course, we can only define this if the values actually exist. So maybe the function doesn't have a supremum or an infimum, maybe it's going to infinity, then of course there's no reasonable definition of that here. Yeah, so we'll restrict that to functions where this works. Not every function might have a meaningful definition of a volume between the graph and the domain. Okay, and then we call a function Riemann integrable over the box B if those two values here, the upper and the lower Riemann sum, if those converge to the same value, if we make the definition, the partition of the box B finer and finer, smaller and smaller. Okay, so the function f is called Riemann integrable over B if, well, what happens here is if we make that partition smaller and smaller, then we would expect the lower bound to go up and the upper bound to go down until they both meet. So we're interested in the supremum of the lower bound, so supremum of sigma minus fp, and we take that supremum over all possible partitions, and for the upper bound we're interested in the infimum, so we find the lowest possible upper bound, again over all partitions of B. And if those are the same, if those agree, so the values converge to the same value if we refine our partition more and more, then we'll call f Riemann integrable. So if that is the case, those are the same. And the value is then of course called the integral of f over B. And that value is called the integral of f over B. And it will be denoted by, as usual, the integral of f of x dx over B. Okay, so instead of having an upper and lower bound on that integral, when you just write the box B below the integral. Doesn't really make sense to specify upper and lower bounds here. Okay, so that's what we'll call the Riemann integral. And of course, that definition begs the question, which functions actually have a Riemann integral? Is there a wide class of functions where this works? For example, continuous functions, maybe continuous functions over bounded sets or compact sets or something like that. Specifically, can we extend that definition of f defined on the box to more general domains? Of course we can. And second important question is, how do we compute these integrals, even over a box? Is there a simple way to compute those? How do we do that? And we'll deal with all of these questions in the upcoming videos. Thanks for your attention for today.